My name is Sarah Sipe, and I work with Dr. Spuchis in the Spuchis Lab Group, which is interested in how proteins and peptides bind metals. One such peptide is the amyloid beta peptide, which binds essential metals such as copper. Amyloid beta in humans can aggregate its hydrophobic residues to form amyloid plaques in the brain, which is a characteristic of Alzheimer's disease. The rat A beta also binds copper but does not aggregate to form these plaques and only differs by 3 amino acid point substitutions. Previous thermodynamic studies in the lab have revealed that the heat capacity of the rat binding to copper is much more negative than the human, which may indicate a more compact structure of the rat peptide. Our hypothesis is that the rat peptide upon binding copper has a more compact structure, which makes the hydrophobic residues more buried within the complex and less available to aggregate. To test this hypothesis, I compared the fluorescence of human and rat peptides in the presence of copper with the hydrophobic fluorophore. 1A ants will fluoresce in a more hydrophobic environment. With the fluorometric data, I noted that there is a larger blue shift with the rat peptide, which indicates that upon excitation, the fluorophore 1A ants is in a more hydrophobic environment. Both peptides decrease in the presence of copper, the intensity, so that means that there is a conformational change where the hydrophobic residues are less available. However, this change is much more notable in the rat peptide at 50% compared to the human at 24%. So this data supports our hypothesis that upon binding copper, the human peptide has more exposed hydrophobic residues for aggregation, whereas the rat is more compact and does not form fibrils.